All right, everyone. Welcome to the DDPS seminar today. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk and please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. Okay, that's about it. Let me introduce our speaker today. It is an honor to host Udaykumar, who is a Roll Carver Professor of Mechanical Engineering and Associate Dean for Research Graduate Programs and Faculty in the College of Engineering at the University of Iowa. He received BT Tech in Aerospace Engineering from the Indian Institute of Technology and MS and PhD degrees from the University of Florida. He has published over 150 journal papers in varied topic areas of biomedical and mechanical engineering. His research focus is on multi-scale modeling and simulation of a wide range of moving boundary problems in thermomechanical systems ranging from phase change, thermal stories, biomedical applications involving cardiovascular and gastrointestinal mechanics, energetic material dynamics and propulsions and munitions, and multi-phase flows at all speeds. He has been supported by grants from NSF, Whitaker Foundation, Biomedical Engineering Grant, NIH, and VA research grants, and multiple concurrent grants from various DoD agencies. Today, Uday will present an exciting topic, which is data-driven multi-scale simulations for materials by design of energetic materials. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Uday by asking one random question, as usual, since it is Friday, in order to recommend a movie for the weekend. Whoever wants to watch movie this weekend. Today's random question is, what is your favorite movie, Uday? I guess you
God.
didn't expect that.
No, I didn't expect that. My favorite movie, would be Apollo 13. I think that's my favorite movie because I love Tom Hanks. I love space, and I always show that movie to my students as a great motivating movie for engineers, because that particular scene when they cobble together the device to scrub the CO2 in the module, is an excellent example of hands-on, in engineering in a very, very high pressure situation. And of course, I force my daughters to watch it as a Christmas movie, which doesn't go over very well in our household. But but yeah, that's my favorite movie. Thank you for
Oh,
that question.
thank you. Thank you for sharing it. Okay, the stage is yours, Uday.
Thank you. Thank you, Yangsu. Yeah, thanks for inviting me. I've been to Livermore. I was saying earlier this year, and it's great to be returning back, although virtually. I hope you can see my screen still, Yangsu and others. Okay, great. Um, so I'll be talking today about data-driven multi-scale simulations for energetic materials. This is work that is funded by the Air Force MURI program, and there are parts of it that are NSF DMREF program grant funded, and also parts of it from ARO. And I do want to mention that this is collaborative work with Stephen Beck, who is actually the deep learning person. I'm a collaborator on this, and Fung, who is also a deep learning person working with Steve Beck at Virginia. And we've been working on this for quite a while now. I would say last 3 or 4 years in the MURI program. So I'm going to try to give a, I was kind of deciding whether to go deep or go broad, and I settled for somewhere in the middle. So it might be, not wholly satisfying for everybody, depending on what they prefer. But hopefully it'll give you a sense for what we have done so far and where we are heading with this. Okay. Okay. So I don't know whether everybody is familiar with energetic materials. I will assume there are others who are not in energetic. So I'll give a very brief account of what we are doing here. So experiments, various types of experiments show that energetic materials uh, are very sensitive, obviously, and their sensitivity depends on the microstructure of the material. So, here is an example of a sensitivity curve. This particular one is called a James curve. On the x-axis is what's called the power flux, and the y-axis is what's called the energy fluence. You can think of the x-axis as being the pressure, shock pressure, and the y-axis as being the shock pulse width or a flyer thickness. So typically these are impact experiments with a flyer coming in at a certain velocity. So x-axis is the shock pressure induced by the flyer, and the y-axis is the thickness or the pulse. And in this plane, the curve separates. Above the curve is critical in the sense that the explosive or the energetic material will detonate, and below the curve it will not detonate. So it's the criticality curve. And you can see that for two different microstructures, class 3 and class 5 of HMX, this is pressed HMX, you can see that the criticality envelopes are very different. That is, the material sensitivity is significantly influenced by the microstructure. In particular, it's influenced by the porosity of the material. You can see that in those microstructures, there are all these cracks and pores and so on. And so the prevalence of these sites determines the criticality curve for these materials. So, and this is a one experiment. There are, scores of experiments that show various dependencies on the microstructure. So this is the fundamental kind of underlying feature of what we're going to try to understand through our work. What we want to do is predictive models for energetic materials, and they're inherently multi-scale because, as I said, the eventual fate of the explosiveness, sensitivity, and so on of the material at the macro scale depends on what's going on in the microstructure, which I shall call the meso-scale for the purpose of this talk. Um, and then, of course, what happens here is determined by the molecular scale properties of the material. What is its strength in particular? What is its equation of state and other thermophysical properties? So there is a telescoping of molecular scale properties onto mesoscale properties and then all the way to macro scale. So we need to build all of this connectivity across scales in order to predictively simulate what's going to happen to an energetic material when it's shock loaded. And my talk is going to be all about shock loading because that's the regime of interest, at least in my work. There are lots of sub-shock detonations and so on, but we won't be covering that type of event in this talk. So fundamentally, the mechanism that leads to sensitivity at the mesoscale is when you load a shock, you form hotspots, and these hotspots typically localize at defects in the material. So these could be cracks or pores or something. There are many mechanisms of hotspots formation from these defects, but in the shock regime or high shock regime, when we're talking about 10 GPa plus or even let's say 6 GPa plus shock loading, the primary cause of localization is the collapse of pores. So these pores collapse. Uh, Strength does matter, but it's nearly a hydrodynamic collapse. And when they collapse, there is jetting and other high-speed phenomena that happen, just like cavitation bubbles. And you form a hotspot, and the hotspots then trigger reactions, and then the reaction front propagates and then fills the material, and that then it's off to the races at that point. And if there is a coupling between this reaction and the shock will then transition to a detonation, and then you get what is called shock to detonation transition, and you get full blow up of the material. So that's the mechanism that we want to capture. Now, this has been for a very, very long time, especially exemplified by the phenomenal work of Craig Tarver and others uh, at Livermore and other labs as well. Uh, Typically these phenomena of the hotspot formation and the mesoscale phenomena leading to the macroscale um, detonation were typically inserted into hydrocodes by using what are called burn models or reactive burn models. There are many flavors of these, and depending on what your speed is, um, you can use many of these which are well calibrated for some particular formulations of energetic materials. But a common one or a popular one is Craig Tarver and others, Tarver, Nichols, a lot of people at Livermore contributing to this. It's called the ignition and growth model, where there's an ignition rate term that is that is dependent on the density and the compressibility of the material, and the rate term, growth rate term of hotspots that is pressure dependent. So this is a semi-empirical model, phenomenological model, where all these parameters, E, X, and so on, are fit to experiments. And so there are lots of experiments conducted for each formulation, and then you get these models. Now, these are the traditional routes of empirical burn models. What we mean by data-driven models is that we are going to use simulations as opposed to physical experiments to obtain these ignition and growth rate parameters, right? So this is the burden then is placed on how well you can simulate the phenomena, and there are lots of uncertainties there for even for quite common materials like HMX and TATB and so on. And then we're going to try to extract data in some meaningful form from the mesoscale simulations, and then we're going to construct these ignition and growth rates from those simulations. So this is the data-driven approach that we're going to take. So multi-scaling is necessary. Just to kind of recap all of that, multi-scaling is necessary. Mesoscale phenomena play a very large role, particularly hotspot phenomena, and we have to somehow bring together these hotspot phenomena into a burn model, and we are choosing the path of a data-driven burn model that is informed by direct numerical simulations. So that's the overall trajectory here. So essentially, to kind of put that in a broader context that applies to a wide range of materials, we are developing data-driven structure property performance linkages for heterogeneous energetic materials. And so that's the overarching theme here. So just to give a sense for how, in our particular case, we are approaching this, and this is, not very uncommon. This would be a standard route for anybody pursuing this activity. So the structure part consists of, images that we might get of an energetic material. This is a pressed energetic material I'm showing here, but it could be a PBX, a plastic bonded explosive, where you would have in the formulation, you would have some kind of binder, and then you would have the crystals, and then you would have porosity. So there'll be three phases there. Here we have two phases. What one would do is, once given a particular microstructure, suppose we want to predict the sensitivity of the material that has this particular microstructure, we can extract by sampling this microstructure or otherwise statistical analysis, we can obtain some idea of what how to characterize its morphology. So we would get some PDFs of void size distributions or void other features of the voids, specific surface area of the voids, and so on and so forth. So that's the first structural analysis part. The second part would be the property determination. So one would do direct numerical simulations to extract properties of the material, for example, its sensitivity. And one would then take those simulations and inform some DD models. And in our particular case, we have developed three different types of DD models, data driven. I'll here I'll try not to say data driven too often. I'll just say DD. Um, and the three different types are what I call message, park, and missile. Um, They're all, of course, appropriately and creatively named to exercise our creativity in this project. Very limited exercise, but those are our models. I will explain what message is, what park is. I will leave out missile. Missile is a model that we just recently uh, have sent out into the world as a publication, and that's still not fully fully established. So I'm going to talk about message and park, two different types of data-driven models. Then we take these data-driven models and feed it to macro-scale hydrocodes as the ignition and growth rates, and then we predict the sensitivity. So there's structure here, the structure part, the property part, and the performance part. So those are the three things, and we have linked all of these in a multi-scale framework successfully in two different efforts. So I'll summarize those two efforts today. Okay, so just very briefly, 10,000-foot view message is a data-driven model that employs Gaussian random process surrogate modeling techniques, and we developed this, you know, for the last 5 years or so, and I'll show some capabilities of that. But I'm going to focus today more on Park, which is a deep learning approach, and spend a lot of time on this one. Missile is something that's a semi-analytical, data-driven approach that we have recently come up with. It's fast, it's dirty. It may not be as physically sophisticated or accurate as Spark and Message, but it does a fairly good job of predicting energetic material sensitivity. So those are the three types of models. And out of all these three models, we extract the very same thing, which is the ignition and growth rates in an IG model framework. And then we can put those into a macro scale code. So the primary goal of RDD modeling effort is to bridge what I call the meso-scale, which is the microstructure, and the macro scale, which is the homogenized material, and provide the closure models for the macro scale. And so it's in this structure property performance framework, we have different packages that we have so far constructed. The overarching package that deals with the structure part is called Matter IQ, which is a Python and PyTorch package. And then we do all the simulations, the mesoscale as well as macro scale simulations with an in-house code called Scimitar 3D, which is a Fortran 95 code that is basically uh, our workhorse solver for lots of problems. So just to describe very briefly in a couple of slides what Scimitar 3D is. So Scimitar 3D stands for solver for computing immersed moving interfaces and transport with adaptive refinement in 3D. And these were, publications that our group put out, as for the last decade or so, various kinds of problems solved with Scimitar 3D. Just to show a variety of things that we have done. So we've done problems of high-speed impact, computation of on real geometries, microstructures, and so on. Damage mechanics, pore collapse, of course, three-dimensional and two-dimensional pore collapse in HMX and other materials. Fragmentation, impact and fragmentation, and blast wave interaction with particles. So compressible multi-material, multi-phase flows is what Scimitar 3D is capable of doing. It is a fixed Cartesian grid Eulerian sharp interface solver, which means that all the interfaces you see here between materials is treated sharply and tracked very much similar to front tracking, but using level sets. So it's a level set based technique. So what you see here, for example, are zero level sets of the plate and an impactor. And so we track explicitly the level sets. So it's a level set based interface, and it's got adaptive local refinement to get features that are very fine. And it's parallelized and uses image processing to process microstructures. So we can go directly from an image to a full-blown calculation on a fixed mesh using Scimitar 3D. So everything on the mesh is described in the form of level sets. Okay, so that's the solver, and we're going to use that. I'm going to not talk about the solver anymore because that's what we're going to use for all our simulations. So the first approach for the DD modeling is message, and this paper came out in 2018, and we've used this for many things since then. And in the message approach, what we do is we bridge the scales between the meso-scale, that is the microstructure, and the macro scale to get the performance simulation. We bridge it using single pore collapse simulations. So this is important as a distinction. These single pore collapse simulations are very fast. You can do hundreds of them in a couple of days. And then you can collect the data from these single pore simulations. And what we do is we get this hypersurface or a surrogate model for the ignition and growth rates of these single pores as a function of the shock pressure, the shock pulse width, the porosity, the diameter of the voids, or the size and shape of the voids. These three parameters are size and shape of the voids. And then we get a surrogate model, and then the surrogate model is used to close the macro scale simulation. So that's message. And so just to show an example of how message works, the workflow of it. Suppose we have the microstructures, and these were provided to us by AFRL, Eglin, from Eric Welle and Chris Molek's group. So we have these pressed HMX microstructures, and we know their porosity, and we know the size of it. We can take these microstructures and we can analyze them to obtain things like the probability density functions of the void size, the aspect ratio of the voids, and the orientation of the voids in the material. Voids are the main features here that we're interested in. It's a pressed material, there's no binder. And so then we can take the statistics of the morphology, and then we also, that's the structure part. In the property part, what we do is we construct these hypersurfaces for the ignition and growth rates in the space spanned by the shock pressure and the void diameter. So we're doing single void simulations. We are varying the diameters of the void, we're varying the shock pressures, and we're collecting data, and we use the what's called dynamic kriging, which is a kind of GRP approach, Gaussian random process approach, to construct these hypersurfaces. So these hypersurfaces tell us about the meso-scale sensitivity of the material. That is, if you subject one pore to the given pressure and the pore is of a certain size, what is the ignition and growth rate of hotspots from that one pore? So somehow we have to take this information and convey it to the macro scale to get the performance aspect of it. So this is just a brief picture of how we populate the parameter space, which is the pressure and diameter of the void. We do numerical simulations here, and these are adaptively done where there's an active learning process that is in the GRP, and that it indicates where we need more data. So we then follow that and do these simulations, and then we have a measure RMSE of to determine the convergence of the surrogate in the hypersurface, and so then we say, okay, now we have a hypersurface that we can use for our calculations at the macro scale. Now, so these are again based on the single pore data. We do the pore collapse, reactive pore collapse calculations. We collect data on the void collapse in a void area, the hotspot temperature, the hotspot area, and the mass fraction of reacted material that comes out of one pore. And using that data, we extract these quantities, the F dot ignition and F dot growth, and these are taken simply from the data, and we calculate the slopes of this curve, which is the mass fraction reacted, and from that curve we determine the F dot ignition, which is the rate of ignition due to a particular hotspot, and then we also get the rate of growth when it settles down into the growth phase. So initially, when the pore collapses, you form this ignition. It ignites the material around it, and so that's the ignition phase between 1 and 2. And then that ignited hotspot, if it survives, if it is critical, it will grow, and then we take between when it's in the steady state growth phase, we take the growth rate. So that's how we get the f dot ignition, f dot growth. Once we have these f dot ignition, f dot growth, then in order to close the macro scale simulation, all we have to do is multiply that f dot ignition and growth by the porosity of the material, and then we get what the macro scale requires, which is the lambda dot ignition and lambda dot growth. And again, those are mean exactly the same things as in Tarver's ignition and growth model. So we kind of plugged into the ignition and growth modeling framework essentially. Okay, so then what we do is using that information of the surrogates, we evaluate the performance, and that is done as follows. So we do, in a coupon, one-dimensional calculations of shock propagation of a particular pressure and pulse width. And once we propagate the shock through the homogenized macro scale material, we need this information of the lambda dot ignition and growth, just like in any ignition and growth model. And what we do is we get that from the hypersurfaces. So for a particular point, if we know the pressure there, we can go in and we know the microstructure, that is the void size and all that. We can go and interrogate the data from the hypersurfaces, and then that gives us the heat release rate in that particular cell. And so we put that into a macro scale, and we look at what happens to the shock. And if the shock rises to the von Neumann pressure, then we say, okay, that's critical, right? And so that's how we construct this James curve. So here I'm showing using message, the method I just described, which is based on the surrogate modeling. I'm showing a comparison between experiment. The black line is experiments done at Eglin Air Force Base for HMX, a particular microstructure of HMX, which is class 5. And so we know, very well characterized microstructure. And we use message, which is the red line here, to calculate the James curve, that is the sensitivity curve. And as you can see, the message does a fairly good job of matching experiment in terms of the sensitivity of the material. So the red line is message. The purple line is Park, and I will show how that works in a second. So basically, our objective is to get this E critical, the critical energy for detonation. And so that's the data that best fits this particular experimental curve. And our critical energy is is in good agreement with the experiment using message. So we can successfully now telescope the microstructural information and predict the sensitivity of a metal as a function of its microstructure. We have done other microstructures as well with success, and that again was provided to us by AFRL. There are a whole other lots of other things we've done with the surrogate-based modeling. We've done inverse modeling. That is, once if you know the criticality, can we determine material properties? We have done that recently, and that's worked out in quite interesting ways. And we're also doing transfer learning. So if we know something about HMX, can we say something about RDX? And that work is ongoing in an NSF project on meta learning. So it's been quite successful. The message route has been quite successful. So the second route of data-driven modeling that we've been pursuing in our Muri project, excuse me, is called PARC. PARC stands for Physics Aware Recurrent Convolution. This is a paper, two or three papers that have come out recently with Steve Beck group. And this one came out in Science Advances this year. So I will briefly discuss what PARC stands for. So PARC is part of a larger effort that is part of a package that we are working on called Matter IQ, which is an AI-based toolkit for materials by design. So PARC fits into that as the DD model. And it's worked jointly, of course, with Steve and Fung. And we are just to give you a very broad idea of what Matter IQ is all about. So in Matter IQ, which is again for metals by design, what we are trying to do is uh, we have different components to the package. The first one is a synthetic microstructure generator. Because we don't have a large number of microstructural samples, we want to take archetypal samples that maybe you have one image for, but then generate an ensemble of samples so we can do statistical modeling of it. And then we can actually do DNS simulations on that ensemble. So that's the synthetic microstructure part. Then we have machine learning models for various purposes, and I'll highlight some of them in the following uh, segment. And then we have actor critic design optimizers, so we can optimize microstructures based on their performance characteristics. And then we connect everything because we have Fortran modules for the solvers. That's legacy modules, and then we have all the Python and PyTorch. We have wrappers that connect all of these into an actual design tool. So that's the framework in which Park sits as the DD platform. So the Matter IQ DD platform is, in terms of the structure, it's a deep learning based approach for generating and experimenting with synthetic microstructures. So we can change microstructures in various ways to conduct these experiments, and I'll describe how that works. And then we do simulations, and the simulations then feed into a deep learning based approach to predict meso-scale dynamics. And then that then feeds into the macro scale performance evaluation. So this loop is basically closed by Park. Um, Let me talk a little bit about the structure part and how DD works into the structure part. Here we can synthesize microstructures using CNNs. And this work has been published in a couple of papers in the last few years, starting from 2020. So basically, we use a GAN approach for synthesizing microstructures. Uh, if you're very broadly, GAN is an adversarial contest between what a generator network and a discriminator network, where the generator tries to deceive the discriminator by generating samples of microstructures, and the discriminator then being the discriminator, um, attempts to push the generator closer and closer to the target image by minimizing an error between the candidate microstructure and the target microstructure. And eventually, through this process, they converge to a particular, hopefully to the target microstructure or facsimiles thereof. So that's the strategy, and it's in the paper by Chun et al. In 2020. And basically, what we have shown in that paper is that we can take one snapshot of an energetic material microstructure and generate many similar microstructure with similar characteristics. So then we can do numerical experiments on them. So these are some ground truth samples of microstructures that we obtained from AFRL. The middle row is a transfer learning based approach and results from that, and the lower row is the final GAN approach that we settled on. As you can see, the GAN approach gives nice clean microstructures. The transfer learning approach can have some local glitches. These are close-ups of parts of this microstructure. And we found that GAN actually produces nice crisp microstructures that emulate the real microstructure. And we also done in that paper, we show quantitative comparisons of various statistics of these microstructures, showing that the black line here is ground truth, and these are probability densities of the void size, aspect ratio, and orientation of the voids. And we show that the GAN approach produces real microstructures with quantitative similarity as well. So we're capturing the characteristics of the real microstructure, and this can also be extended to 3 dimensions. The paper also addresses 3D microstructures, in this particular case of sandstone, where you can take the ground truth sandstone microstructure and synthesize it and generate ensembles of synthesized microstructures. And these are showing 2D slices of these microstructures and quantitative comparisons. This is very dense. I won't go into it, but you can look at various metrics of the quantitative characteristics of the real microstructure and the synthesized, and we show that the synthesized microstructures capture the characteristics of the real microstructures fairly well. So that's the structure generation part. Now, what that allows us to do in a materials by design standpoint is that we can manipulate the microstructure. So once we have the baseline microstructure that emulates the real microstructure, then we can turn knobs literally in the generator. Basically, we are modulating the latent variables, and by modulating the latent variables, we can change the structure of the material. So, for example, just to show one instance, by performing a particular operation here, we go from this initial small microstructure, small grain size microstructure, and we can manipulate the latent variables to go towards finally to a larger microstructure. And we can do this for various other things as well. For example, here we can control the orientation of the crystals or the voids. In fact, we've shown that depending on the void orientation, the sensitivity of the material can change massively. Voids that are oriented along the shock propagation direction tend to be more sensitive than voids that are oriented normal to the shock propagation. So we can actually investigate effects of orientation of voids and so on. And so we can now manipulate the microstructures virtually to get different void orientations. We can also look at mixtures of sizes by modulating the latent variables. The uniformity, if we toggle the latent variables in a certain way, we get bimodal mixtures and so on and so forth. So we can now control the microstructures virtually. And these are done, these are a picture of the latent variable weights here. And for different weights of the latent variables, we get different crystal sizes, void sizes, and so this allows for flexibility in making different microstructures. We can also paint microstructures using this approach, which is to say that we can spatially vary the microstructure. So this is microstructure that was generated with small grains on one end and large grains on the other end. So we can do that. We can also paint microstructural the regions. So here we have taken the Hawkeye, which is the University of Iowa symbol, and we've gotten permission to do that from our university, which is very important. And what we show here is that we want to put large crystals in this yellow region and small crystals in the black region. So we imprinted that Hawkeye image onto this microstructure. If you can see here, these are the large crystals, and then the surroundings are small crystals. And we actually 3D printed this. We have a depth score grant with a collaborator, Professor Sean Song, and he does pressure jet printing. And so this is sugar crystals, of course. Being a university, we can only handle sugar. And so here you can see that there's the Hawkeye's larger crystals are printed over here, and these are all small crystals. And just zooming into this region here, you can see the large crystals of the Hawkeye symbol. So we can actually transmit our microstructures to somebody who does 3D printing and actually do that. And then, of course, finally, we use these microstructures, the synthetic ones, and look at the shock response of it in simulation. So this is for small crystals and it's for large crystals, and you can see that the growth rate of hotspots is very different in the two of them. So that's the facility. Now we're also doing other things. Irene Fung, who's actually at Livermore for the summer, Irene is working on manipulating microstructures to explore design in the following way that she's actually um, uh, she can actually modulate damage on the microstructure. So she's coming up with a deep learning approach so that we can take a input microstructure and we can actually remove all the damage from in there and then re-damage it in a controlled way so that we can insert as much damage as we want, because we want to study the effect of damaged microstructures on their sensitivity. So that's the idea over there. Okay, so in fact, I will actually, in the interest of time, skip through Irene's work because I want to get to Park. I think I'm actually um, Youngsu, how much time do I have?
Um, maybe 5 to 10 minutes.
Okay,
Well,
fine.
10 minutes.
I might
Let's say 10 minutes. Yeah.
Okay, I might take 10 then because
Yeah.
I okay. So in Park, basically what Park does is that it learns from DNS simulations and then it can actually do predictions once it's learned from it. So we are asking questions like can we train an AI model to assimilate the physics of energy localization? Can an AI model serve as a surrogate for DNS calculations? And can AI models provide physical insights? So we don't want it to be a black box. We want interpretability. So we want to get information out of Park. And as I said, Park fits into this overall framework where as a data-driven modeling uh, entity. So this is the DD model that we're using in the larger materials design optimization and discovery framework of Matter IQ. So Park, basically, the idea behind Park is that we are going to formulate the shock-induced hotspot evolution as a dynamical system. That is, we pick this variable x from the physics of the problem, and in our particular case, we pick x to be a function basically consists of a vector of the temperature of the hotspots, the pressure in the domain, and the microstructure, because the microstructure evolves. So it goes from becoming from voids to void collapse and then eventually to become hotspots. So we want to track the evolution of all three things: the temperature, the pressure, and the microstructure. And so we train the model to learn those three aspects, the evolution of those three aspects from numerical simulations. And that's the idea behind Park. So basically, Park is assimilates knowledge of how that evolution of this field X takes place. Um, and uh, and we formulate it as a recurrent neural network where we have differentiator and integrator networks, and these differentiator and integrator networks assimilate the derivatives of the variable x, and then they perform the integration, and the time evolution is assimilated within Park to eventually predict what happens at the end when the hotspots finally um, grow and merge in the material. So just to show an example of a Park calculation, so this the top row is DNS for this microstructure. This is the Park prediction for that microstructure after training. So you can see that, sorry. Um, so Park does a good job of predicting what happens, the hotspot, the location of the hotspot, the frequency of the hotspots, and so on. And the advantage is that while a DNS would take days on a HPC, Park would just be really quick prediction. So it predicts the time evolution of hotspots. And it also predicts the pressure. As you can see, the pressure is not as well predicted as the temperature because the pressure has smaller gradients than the temperature. The temperature is much sharper. But it does a fairly decent job of predicting the pressure evolution as well. So this X, which is, and the void collapse evolution, the microstructure evolution. So this is Park exercised on many different microstructures. The lefts are ground truth and the rights are predicted. I know it's very difficult to see this, but basically the overall message is park predictions are in good agreement, and this is a quantitative comparison. So for various microstructures, we've worked park and we've done DNS, and the confidence intervals here are the microstructural variability due to microstructural variability. So this is the hotspot temperature versus time, the hotspot area versus time. As you can see, park in the mean and also in terms of the distribution, park produces a good hotspot area evolution over time in good agreement with the ground truth. The rate of change of area of the hotspot versus time is also in good agreement with the with the ground truth. So we get the hotspot dynamics right. Now we've used this park model to do the multi-scale, full multi-scale. So basically that came out in a paper in PEP actually, just recently, and where we can take a macro scale image sample, we can do the statistical analysis of it, we do DNS simulations, we train park, and then park predicts the hotspot growth rate and so on, and we feed that to the macro scale simulation and predicts SDT and the criticality envelope. And this is the James envelope of predicted by message. So message, sorry, park. Park is the purple one, message is the red one. So the two approaches, somewhat in the low pressure range, as you can see, there is more sensitivity and they straddle the experimental data, while in the high pressure range, they're in very good agreement with each other and also with experiment. So this is a a demonstration that we now can put all of the pieces together in a multi-scale framework. Now the question is, of course, did we learn physics or is it just pictures? And so can it tell us something? In order to investigate this, we tested Park in many ways. First, we tested this to a off-the-shelf physics naive models for learning, and we showed that Park does a better job, or in fact, some of the physics naive off-the-shelf codes that we tried this on, did not match with the ground truth, but we are able to match closely with the ground truth. The second thing we tested was looking at time evolution beyond training. That is, we train Park for a certain time and then we let Park go. And then we do the DNS for those longer times and see if it captures the evolution correctly beyond the training time, which is an extrapolation. And Park does that successfully. Then we also looked at outlier microstructures. We had trained Park on a certain set of microstructures, and then we picked microstructures, parts of the microstructure that were quite different from what we had trained Park on. And we looked at whether it can actually predict the behavior of those, sensitivity of those. For example, very large crystal like that, we do a DNS, and then we also look at Park and ask whether Park can predict where the hotspots are. We also tested Park to unseen loading conditions. That is, we trained Park on a certain set of pressures and we looked at other pressures. And there as well, Park captures the physics and gives us the correct hotspot growth rates. So aside from this, we also asked the question, can Park tell us some information about the physics? So in order to do this, we asked the question from our simulations, we noted that only a small subset of voids generate hotspots. And why is that? What is particularly interesting about those critical voids? And can we get information about this? So we used the saliency map, which is a derivative of the temperature with respect to the microstructure. And we have these two fields, the temperature field and the microstructure field. So we can then establish the sensitivity matrix. And that is what I'm calling the saliency map field. And so if we threshold the saliency map field, we find that the saliency map tells us which voids went critical and formed hotspots. And so we can superpose this on the microstructure and we can examine these voids that cause the hotspots. As you can see, the vast majority of voids fail to produce hotspots. So then we're asking what is special about these critical hotspots? And we zoom in there and we try to correlate the morphology information with the sensitivity information. And what we find is, by doing this analysis, is the following, and it's actually, it matches with the physics that we had earlier learned in various other works. which is that these are critical voids and these are the non-critical voids. And as you can see, the critical voids don't look terribly different from the non-critical voids. You know, but there are subtle differences, and the subtle differences are as follows. So if you look at the average void diameter of critical voids, they tend to be smaller than the average diameter of the non-critical voids. If you look at the aspect ratio of the critical voids versus non-critical voids as the elongatedness, they're not terribly different. But if you look at the orientation, it has a very strong effect. So critical voids are nearly horizontal with respect to nearly horizontal with respect to the shock direction, whereas the non-critical voids are oriented much more parallel to the shock direction. So that orientation has a significant impact on sensitivity. Okay, so I think I can summarize this now. So basically, Park can predict well the response, and we used about 35 DNS simulations. So the data is not terribly large, and Park manages to gather information from that. And we showed that Park does produce physically meaningful and physically insightful results that we can interrogate. And so I think there are further developments of Park that I will not go into right now. We are working on improving accuracy for weak hotspots and other accuracy issues and robustness issues. But so let me summarize, finish by putting this slide on Matter IQ. So basically, we now have the ability to manipulate structures. We can do simulations that feed into data-driven models, and we can predict the macro-scale phenomena of sensitivity in a multi-scale setting. So I'll finish there.
Thank you. Thank you so much for the wonderful talk, Uday. Let's have a Q&A session. I don't see any question in chat room. So if you anyone has questions, please unmute yourself and ask. I don't know, you can raise your hands or unmute yourself and just speak. Either way. Anyone? Larry, yeah?
Yeah, I was wondering, had you looked at applying your technique to samples of varying initial density, where you might have porous materials versus very dense materials?
Yes, Larry, thanks for the question. We did 2 microstructures. You know, we don't have access to too many samples. We did an R10 microstructure and a class 5 microstructure, both pressed HMX. And our predictions of sensitivity were in accord with experiments on those 2 microstructures, both done at AFRL Eglin. We are actually working on a third, now we are doing PBXs, and we're working on a third microstructure as well, which is very different from those 2 microstructures. So the porosity is much lower. So we are doing that right now.
Yeah, very impressive work. Thank you very much.
Thank you, Larry. Just to add clarification to that, the R10 had a 7% porosity and the class 5 had a 14% porosity. So quite different microstructures.
Okay, thank you.
Thank you.
Okay, we have another question in chat room by Cooper. He asked, did you look at the difference in the surface area for the critical versus non-critical voids?
Surface area. No. We looked at diameter aspect ratio, right? So aspect ratio is not terribly sensitive to the aspect ratio. It is sensitive to the diameter. So the surface area does matter. And in fact, this is common knowledge. The specific surface area does matter. So the smaller voids tend to be more sensitive than the larger voids for a given aspect ratio. So that's our finding. So specific surface area for a given porosity, then that means that there will be a larger surface area, specific surface area with smaller voids. So that's specific surface area is important.
Okay.
And it's consistent with both Park findings as well as message findings.
Thank you.
Thank you.
You had a curve, the results of the message and results of the curve from the Park. One is underestimating, the other one is overestimating.
Yeah.
In physics point of view or application point of view, which is more valuable? Is underestimating is better or overestimating is better in criticality curve you showed?
Well, I think having neither would be best, I guess. But I know I sort of have it in. So let me actually, if I can, oh yes, you're mentioning this one, right?
Yeah.
So,
previous one. Yeah, that one. Yeah.
This one, yeah. For some reason, hang on a second. Push that up. Okay, yeah. So this region is the most difficult part. So this one is actually fairly straightforward to predict, which is heartening that we can do that. But I would rather have good predictions over here. The problem over here is, and we're working on this, is that over here it's not truly hydrodynamic. The void collapse here. So there is also physics missing, I think, in this area of the plot. Because as you approach about 5 GPa and so on, you can get effects of shear bands and other strength-related aspects of the material. And those are not terribly well modeled currently in our work. And we are trying to remedy that by using better physical models for this to represent the strength. And we made some progress on that, so that's ongoing work. But I think so. I would in answering your question, Youngsu, I don't know if this is particularly issue with the DD models themselves, or is it actually a misrepresentation of the physics there? Until we fix the physics, I would not know what to say about those two things.
Okay.
So, yeah.
Yeah, it looks like if you average those two, then
you'd be in good shape. Yeah.
Uday, this is KO. I've got a couple of questions.
Yeah.
Go ahead, KO. Yeah.
In regards to Park, I didn't see a void-void interaction term or some kind of provision for void-void interaction. What role do you believe that plays in what determines a critical defect morphology, size, orientation, whatever?
The void, in my estimation, the void-void interaction part is inherently learned by Park. Whereas in the message model, we have to have another surrogate model, which we have, and we have to insert it into message, which we have done in order to get these curves. So in message, we have to make an effort to include void-void interaction because it relies on single void calculations, whereas because Park relies on a full DNS, and the full DNS already has the void-void interactions in it, I think Park actually takes that into account. Now, having said that, we've done recent work that shows that for small void sizes, by which I mean about a 1 micron diameter void sizes, void-void interactions may not be a terribly strong effect. For larger void diameters, we find void-void interactions a very strong effect. So I think in this instance, because the void sizes in class 5 center around about 0.5 micron, I don't know if the void size interactions will play a major role in this, if in the discrepancies that exist in the predictions for this particular case. But I think Park actually should take into account void-void interactions.
Yeah, of course you have the ignition and ignition criticality, and then the growth, and there are opportunities in both phases to be able to take place. Yeah, I mean, I think that it seems like some kind of provision for part going forward that considers that possibility, but clearly having first, as a first order, the void itself is probably one of the I guess, like you're saying, one of the most important things.
Yes.
In regards to the low pressure regime that you're pointing to, do you believe that there are fundamental mechanism changes? It seems like you're implying that by saying over a certain pressure regime, it's hydrodynamic, and under that could be more of a viscous and other kinds of interactions that perhaps we don't normally encounter, whether it be surface physics or other kinds of modes or what have you.
Right.
Have any thoughts about that specifically, mechanism changes?
Yes, I certainly do actually. So if you look at where we are about 5 GPa, 5 GPa is about the pressure at which we find that most the voids are sort of borderline. They're not collapsing in full hydrodynamic mode. And if we do the calculations of that, in fact, with the Johnson-Cook model, the rate dependent model, and so on, KO, that you guys actually have published on, we find that there are shear bands, and there is a significant change of mode of collapse of the void from whereas for high pressures it's hydrodynamic, in the jetting mode. For the lower pressures, it tends to be more of a closure mode. In fact, as you go to lower pressures, it closes with a sideways pinching mode rather than a jet mode. And in the sideways pinching mode, the shear bands play a very large role. So I think there is definitely some kind of a mechanism transition, because below about 5 GPa or so, you really don't get criticality. So the void may collapse, but it collapses so weakly that you don't get criticality. So there is something here happening, both in terms of, well, first of all, in terms of the mode of collapse and the strength of the material kind of playing a role. But secondly, also, I think this region is much more sensitive to the chemical kinetics models, and we've done quite a bit of examination of that. Which this curve that I'm showing, even for message, can move all the way out here with a low, with a one chemistry model, reaction chemistry model, and all the way to the other side with another chemistry model. And we found that, in fact, doing an inverse analysis, that the best fit to the experimental data from the chemistry models comes from the Henson one equation global kinetics model. So that also plays a role, clearly, the chemical kinetics, because the temperatures here, due to void collapse at lower pressures, tend to be borderline. So the reaction kinetics model is very sensitive in that region and predicting the criticality. So there's a lot going on in that region that really needs a lot of looking into, and that's actually the interesting region for us, because that's the threshold, and if we can predict that correctly, then that's not a terribly great model. So this variation here is of concern, but I would first try to get the physics right before trying to figure out which DD model is better in that sense. So there's a lot going on there, Kyo. Much work to be done in that region.
Thank you, Uday, and great talk.
Thanks, Kyo.
Any other questions from audience? Well, I have a rather a comments than questions about the naming, physics aware. There are a lot of active research going on in physics simulation and also the machine learning side. One example is physics informed neural network. And another one is more traditional way of bringing the physics into the data-driven model is using the projection-based reduced to the model. It's clear that why they are calling their data-driven method is physics-aware, physics-informed, because they actually using underlying governing equations to build a data-driven model. But your Park model, I don't see that. And I do see that data is generated from DNS model, which is, solving the physics governing equations. But in data-driven, the physics model is not directly integrated into the model. So yeah, there is something debatable here, whether you can call it physics aware. I know that you have shown that, generalizability at the end, your Park model actually, predict some physical characteristics, right? Some ratio, the rate, but still, I don't see where the physics is incorporated in the process of building the model itself.
So, yes, so this has come up quite frequently, especially with the PIN framework and so on. So clearly in PIN there are in particular the divergence-free velocity constraint is built into the network, right?
Or they not only that, actual governing equations they are incorporating into the data-driven model.
So we are not absolutely. So in some sense we are much more, or somewhere we are in between that part, that philosophy of making the new network emulate the full governing equations and the reduced order modeling, in the sense that we are trying to learn, because it is intended to be a bridge between the meso and macro scale simulations. We are abstracting from the meso-scale what is physically relevant to the macro scale. In our particular case, what is physically relevant is the temperature field, the pressure field, and the microstructural evolution. The system of equations we are solving is very, very large. It is a reactive, fully compressible system with interfaces, full interfacial dynamics. We don't want to be in the situation where we impose upon the network the need to solve that entire system of equations. That's not the idea here. The idea is to use some of our expert intuition in picking the physics that needs to be learned by the network. And we couple those three elements, the temperature, the pressure, and the microstructure within the vector X. And so we are trying to look at the coupling of the physics between the shock and the hotspot and the void. And in that sense, we are keying in what is required in terms of physical ingredients into the network. And we're making it actually emulate the evolution of the process through the differential equations. So, if we don't do that, we don't get the results for the hotspot evolution that, as I've shown, we don't get the correct results. So, and the other tests I showed that we are actually capturing physics and we're making, extracting insights that are physically meaningful and match with expert knowledge. I think in those senses, what we have is a physically aware system. It's not physics is not the same as a physics informed neural networks. That's not the philosophy. The philosophy, it's not a reduced order model. It's using physics and physical knowledge and integrating that into a neural network that produces for us what we need, which is taking the information from the meso-scale and transmitting it to the macro scale. So that's my overall kind of outlook on what we are trying to do.
Okay. Is there any other question? Well, I mean, we actually passed the 10 minutes to.
Sorry.
No, sorry. I mean, it means, we are very interested in your work. So I think it's a good time to wrap up. Well, let's thank our speaker, Uday, for the wonderful talk and wonderful Q&A sessions. A lot of applause there. And yeah, I mean, let's wrap up here. Thank you, everyone, for
Thank you so
joining.
much.
And if you do have a question, please email Uday directly. I'm sure Uday is going to answer your questions, diligently.
Yes, welcome.
And then, yeah, and then, of course, the future collaborations between Lawrence Livermore and then your group. I think it's already going on. So let's continue to do so.
Right.
Thank you, Uday, for the wonderful
Thank
talk.
you so much. Thank you, guys. Bye-bye.